me. I gave him that talk. Okay, so I will talk about Santiago and the mathematics we did and didn't do together. And what I will tell will have nothing to do with the title of my talk. So we will see. Okay, so the first time I met Santiago was in July '86, and it was the second colloquium of the Mexican Mathematical Society. The first one had been on algebraic topology. And in fact, the proceedings have been published as notes in mathematics, which is quite good. And in that, we realized with Santiago that we had been working on the same object for different purposes, but with a common source, which was a paper by Marc Chaperon, which was about the topology of holomorphic flows with singularity. Can you read me? Okay. So, maybe. So that's what the paper, Camacho-Kuiper Alice paper was about, is linear systems of complex differential equations. Okay, so you have a diagonal matrix lambda, and you are studying the topology of the leaves of the foliation it defines. That is the images of the solutions. You have global solutions, of course, which are given by the exponential, and then the topology is not so simple. And what they did in that paper was so they made a hypothesis which is generic, which is that the eigenvalues are independent over R. So the line between, they are simple, this, and the line between them never contains the origin. Okay? And in fact, there are two cases. The first case is when the eigenvalues do not have zero in the convex Hell. That's called the Poincaré domain, and then everything is simple. And the classification is not complicated. The interesting case is that of the Siegel domain, which means that the convex Hell of the eigenvalues contains zero in its interior. It's in the interior because of the hyperbolicity hypothesis. And then what they did was show that there is a continuous invariant, which is rather surprising, and which of course depends only on lambda, of such linear objects. Okay, so in order to study such the structure of such foliations, I think it's Camacho who introduced this function. So this function which is something like a Lyapunov function for the flow. It means that every orbit of the flow, the complex flow, time is complex, intersects a level of this function transversely at exactly one point, except except at most one point, I mean, except for the origin, which is a degenerate orbit, and we don't consider. Okay? So, what Santiago was interested in is the zero level of this function. So the drawing I have made is the real analog of what he did in the complex domain. So in that case, so you take real zj's and real lambda j's, and then you see that the zero level here, first in the real case, you see you have the stable space of lambda, which is the horizontal axis on my drawing and my picture, and the vertical axis is the unstable space. And you see that the union of these two spaces is the space of the so-called Poincaré orbits, which are the orbits which are adherent to zero. Or I don't know, maybe zero is adherent to the orbit, but anyway. And the other ones, the other leaves or orbits, as you wish, are the Ziegel leaves. They are the ones which are bounded away from zero. Okay, and you see that the red thing, which is the zero level of f, intersects every Ziegel leaf at exactly one point. And the same happens in the complex case. Okay? And Santiago was interested in the study of these Ziegel leaves in a slightly more general case, which is called the weakly hyperbolic case. In fact, that's my terminology. It's the case where the segment between two eigenvalues never contains zero. So the eigenvalues might be the same, multiple, but what's important is that the segment between them doesn't contain zero. So what Santiago studied is the topology of the space of Ziegel leaves. That is, you take that cone, the zero level of f, and you just take away zero because that's not interesting. And you see that, in fact, if you know the topology of the intersection of this zero level of f with the unit sphere, you will know everything because you have a natural action of the positive real numbers on the leaves of the foliation by multiplication, because these are the orbits of the linear vector field. Okay, and therefore he studied the topology of such objects, and what he got. So it's in his paper in the proceedings of that second colloquium of the Mexican Mathematical Society. He showed that the topology of these objects they could be products of spheres, which was not so surprising, but they could also be connected sums of products of two spheres, which was more surprising. Okay, so in fact, the proof was a rather nice piece of topology using the H-cobordism theorem and so on. And maybe I should say what he did a bit later with the same object. So you see, here we have taken the quotient of the space of Ziegel leaves by the action of the positive real numbers. But there is also a natural action by the non-zero complex numbers. If you multiply a leaf by a non-zero complex number, you obtain a leaf. Okay, so so this amounts to quotienting the intersection of the zero level of F with the unit sphere by the natural action of the circle, okay? And then what you get, you get a compact manifold, and it is holomorphic because it's the quotient of an open subset of Cn, that is you take away the union of the Poincaré leaves, and that's a closed subset, and it's the quotient by a holomorphic action of C cross C star, that is, the C is the flow, and the C star is the action, natural action of C star over Cn. Okay? And these objects turn out to be quite interesting, and this is work of Santiago with Alberto and Hopf, because they provide examples of compact complex manifolds which are not symplectic, which means that they cannot be endowed with a symplectic form. Because if you have a symplectic form, then you have a trivial H2, I think, and that's the reason. Okay, and this was published in that paper in memory of Ricardo Magne in the Boletim da Sociedade Brasileira de Matemática. Okay, so it's a rather famous work. Okay, so how did I get to work with Santiago? Well, in fact, I had used this same function f to do something quite rather different. So it has been published a little later in the Publication mathématique de l'IHES. So in fact, in that paper there were, among other things, two results. One was that, so I still have the same notation. Lambda is that diagonal linear vector field, okay? Then a question which was asked by Camacho, Kuiper, and Palis was whether a nonlinear germ of a vector field at zero in Cn with lambda as its linear part could be linearized in some sense or some other. And what I proved is that it's two things. First, I introduced a result which is for CK conjugacy. So what is CK conjugacy? Or maybe one should say conjugation, I never know. It's that you are allowed to make CK changes of variables near the origin in Cn, viewing Cn as R2n, of course, and you say that two germs of holomorphic vector fields are CK conjugate when the local complex solutions of the equation associated to one of them are transformed into the local complex solutions of the differential equation defined by the other by the change of variables. So the result is that you can, using a CK change of coordinates, you can make every such holomorphic germ into what is called a normal form, that is a polynomial vector field which has lambda as its linear part and which commutes with lambda. And in general, generically on lambda, a normal form is just lambda, but you have other cases. Okay, so in fact, in the Poincaré domain, as always, this is essentially easy and well known. It means that because you instead of CK change of variables, you can use holomorphic changes of variables, and the result is due to Dulac. Okay, but in the Siegel domain, this result is extremely different from what you get for the holomorphic classification, because for the holomorphic classification you have small denominators which prevent the normalizing series from converging. And this, what I proved here is that for CK conjugacy, with K as large as you wish, these small denominators are, so to speak, invisible, provided lambda is weakly hyperbolic. Okay? So it's something you do not see from the viewpoint of differential geometry. So it's a holomorph, an analytic thing. Okay? So I proved this result, and from this I deduced something which interested more people. It is that if lambda is hyperbolic, then a germ of vector field with lambda as its linear part is topologically linearizable, which means that it is topologically conjugate to lambda. It means sending complex solutions onto complex solutions. You have a local homeomorphism which does that. Okay? In fact, what I got was rather better result, because the conjugation I constructed was Hölder continuous for every Hölder exponent, and it implied the Camacho-Kuiper-Pallis conjecture, which was weaker. It said that such a vector field X should be C0 equivalent to lambda. Equivalent means that you are sending one foliation onto the other locally without considering the way they are parametrized by time. And in my result, you keep track of time. Okay? So maybe the reason why I'm telling you this is that, going back to page 2, so you see in that drawing, the red part was the zero level of F, and the green part was what's the name? A non-critical level of F, a regular level of F. Okay, and what you can see is that it intersects some of the Poincaré leaves and not some of the others. Okay, so maybe I should explain how I proved these two theorems. The first one was obtained. So you see, in the complex case, you have an analog of the union of the stable and unstable manifolds, which is just the union of all Poincaré leaves. Okay, leaves which are adherent to 0. And what I proved for the CK conjugacy theorem is that first using a holomorphic change of coordinates, you can put. So that was the result which was in the proceedings of the meeting in Mexico and Chapala. Using a holomorphic change of coordinates, you can put your vector field into normal form all along these Poincaré leaves. The union of the Poincaré leaves is in fact a union of coordinate x's, okay? And a normal form, because it's the sum of lambda and something which commutes with lambda, preserves all these things, okay? And then, in the real case, for example, the stable and unstable manifolds, spaces, of lambda, are preserved by the normal form, are the stable and unstable manifolds of the normal form, okay? So first you can, what I call the preparation lemma, you can put along these this set of Poincaré leaves, you can put your vector field into normal form by a holomorphic change of coordinates. And once you have that, and you can put it into normal form to an arbitrarily high order, okay? And if the order is high enough, then you can construct your conjugacy by just asking the conjugacy to be the identity on the green thing, that is a regular level of f, and then telling that it's a conjugacy, it will define it almost everywhere. That is, here you see in the real case it's the complement of the unstable subspace, and then there is an extension result which tells you that if you had enough contact between your prepared vector field and the normal form all along the Poincaré leaves, then it extends to the missing part. So in my drawing, that's the unstable manifold. Okay? And in fact, to prove the second theorem, I used the same idea, but I started from the normal form, and then I killed the nonlinear terms using the same device, and the fact that the normal form has a rather special flow, which is just obtained by taking the formal flow. The formal flow exists for sufficiently long time, so to speak, to represent the local C action accurately, and then you get your conjugacy as a convergent power series in variables which are of the form x logarithm of absolute value of x or something like that. So they are Hölder continuous for every Hölder exponent. Okay, so in fact, what I was planning to do with Santiago at the time is get rid of the H-cobordism theorem and also try to classify a more general situation, because what I have showed here for C actions, in fact I did for RK actions, local RK actions. So you take K commuting vector fields, and under genericity assumptions on the linear part, you can show the same kind of theorem. Okay, I will not go into that, but then I had used the analog of this function f, which amounted to looking at levels of some kind of a Lyapunov function, which was a function with values in Rk or the dual Rk, and these levels were that these functions were in fact very special quadratic forms, because they were diagonal. Their components were all diagonal in the same basis. Okay, and I thought I had the technology to study the topology, because when I had been proving these results, I had looked at things in some kind of charts, which were not exactly charts, but there were simple things, local things, which were essentially products of spheres by vector spaces, and I had a gluing process given by the action, and so I thought that using this gluing, we could study the topology of these manifold by brute force instead of using some fancy result in differential topology. And then, so the chronology, maybe I should stick to the chronology. So our next meeting was in '87 in Cornell. Okay? And in fact, it was a meeting on holomorphic dynamics, and I was telling the same story I am telling you because I had no other. In fact, I had been working in symplectic topology and not in this subject. And Santiago had some new results about iterating polynomial maps, which were not holomorphic maps, real polynomials. And in fact, in Cornell, we happened to become friends because first we had many common tastes. One was for food, and we were, in fact, we were in Cornell. You know, there is a cooking school, and we had breakfast in a big building, and it was full of food, and you had one ticket and you could taste everything. That was terrible. And so both of us behaved badly in that respect. And also there was a piano, and also there was a good old Steinway at Hubbard's place. And at that time I was really thinking of quitting mathematics for music, I mean for composing music, not playing music. And so I had much music in my mind, and I played a lot, and Santiago played also, and I was amazed that he had such a musical personality that he would produce about the same sound on every piano. And that's really rare. I mean, it's like Fort Wagner. When Fort Wagner was conducting any orchestra, he would produce the same sound. That's incredible. It's something which has to do with your intimate personality. So I was amazed by that. And so we became friends. And I invited him to Palaiseau, because I was working at the École Polytechnique at the time. And then we had that program of gluing simple things in order to obtain these spaces of Ziegler leaves, even for arcade actions and so on. And the program never worked, because everyone I was talking about gluing, Santiago was falling asleep. And so nevertheless, we had a good time, but from the viewpoint of gluing, it was desperate. Okay, so next, I went to Mexico. So that was at the end of the year 87, and we still had that gluing program, but in the meantime, Santiago had been to the so-called Waddington Symposium on mathematical biology, and he had met Christopher Zeeman, and Christopher Zeeman had an idea to, in some sense, put the theory of dynamical systems into the framework of what's called elementary catastrophe theory. That is the theory of smooth real functions on manifolds. Okay? So, in fact, what happened is that we worked on that instead of gluing. And it was really fantastic, because we were going to fancy restaurants, and he would ask me very good questions, because he has a clear mind, and surprisingly I could answer them. So it was on napkins and so on, and we solved the little problem he had, which was not so little a problem. So let me explain what it was about. So in fact we did not publish much in that respect, because we published a note au compte rendu with Christopher Zeeman and his student Charlotte Watt, and then there was some conflicts between Zeeman and myself, not a conflict, but, well, which had nothing to do with mathematics, but we stopped collaborating. But, so what was the question? You have a compact-oriented manifold without boundary and a Riemannian structure on it, and you have a flow on it, which is the flow of a smooth vector field X. So you see, imagine that it has what is called a smooth invariant probability measure. That's a volume form, whose integral over the manifold is 1, or total volume is 1, and which is preserved by the flow, by any time of the flow. So this, the last condition, writes in terms of Lie derivative, of course, the fact that the Lie derivative of omega with respect to x is 0, and as omega is an n form on an n manifold, this, by the Cartan's formula, it means that the differential of the interior product of omega by x is 0. Okay. Then, if you look at the equation which is satisfied, you take the push forward of the form by the flow, and you call it omega t. Then, if you pull it back, of course, you will get the initial omega for every t. So you get that, and now if you differentiate with respect to time, you get that the Lie derivative of omega t with respect to x plus the derivative of omega t with respect to t is 0. Okay, so this looks like a nice equation. Unfortunately, you know that invariant measures, which do exist in general, are not unique and are not smooth. Sometimes, okay? So the idea of Zeeman was to put a small diffusion into the problem, and consider the analog of this equation, the equation satisfied by omega t, adding minus epsilon delta omega t to it. That's called the Fokker-Planck equation with epsilon diffusion. At least that's his terminology. And you see that this equation can be solved rather easily, because after all, what you're considering is a linear differential operator, and it turns out that it's about the same theory as for the heat equation, because epsilon may be small, but nevertheless the minus epsilon Laplacian of omega t is the dominant term in the story. Okay, and then what happens is that you just write down the solution of your Fokker-Planck equation for positive t. For negative t, it's a catastrophe. The Laplacian I'm taking, by the way, is Laplace's Laplacian and not the Laplacian of G orbiters, which is its opposite. Okay. Okay. So it means that this flow is well defined, and the exponential of t times epsilon delta minus the Lie derivative with respect to x is well defined, and for every positive t, and it is a strictly positive operator which preserves the simplex of smooth probability measures. So I'm not going into it, but you have to do some functional analysis with the Sobolev spaces and so on. It's not difficult, because if you think of M as a flat torus, then you have Fourier series, which are just an expression. You can express forms as the sum of Fourier series in an eigen basis for the Laplacian, and then you can do the same in every Riemannian manifold, except that you have to take an orthogonal. Okay, and then you go to the limit when the Sobolev exponent goes to infinity to get smooth probability measures. So this is a compact strictly positive operator. So strictly positive means that it takes any non-negative form of maximum degree on M onto volume form. And it preserves the total volume. So in particular, it preserves the fact that it preserves probability measures. And now you have a very useful theorem about such objects, which is called the Perron-Frobenius theorem. Those of you who know about, what's the name? Markov chains, it's used there. Exactly, it's an easy case in fact, because so you have this red thing, which is the simplex of non-negative smooth forms of total volume 1, and it's taken into itself by this operator, and what happens is that there is a unique fixed point. So the fact that there is a fixed point, you can do it in several ways. In finite dimensions, it's easy. You can use the infinite dimensional version of the Brewer, fixed point theorem, and then it's unique because in the direction of a constant volume, you have a contraction because the operator is strictly positive. So okay, so that's simple. And so what was the idea of Zeeman is that you have to each vector field you associate this unique fixed point on the affine space of forms of total volume 1, and then you can represent it with respect to the Riemannian measure, or the Riemannian probability measure, if you normalize it. And so you get a function, a smooth function. And the idea of Zeeman was to just lift the theory of singularities of real functions, that is these densities, to dynamical systems using the map which to x associates omega x. And in order to do this, you needed to know that this map is a good map. So what we proved with Santiago during our meals is that the map which to x associates omega x is a smooth locally trivial fibration. Okay? And we also proved an analog for discrete dynamical systems. You take diffeomorphisms instead of vector fields. Okay, and the reason why we collaborated with Christopher and Charlotte is that the second half of the result had been the subject of Charlotte's thesis, so we had to not step on her feet. Okay. Okay, so that's okay, now I am going to use this functional setting as a transition to what we are trying more or less to do together for some time. So maybe I will be a bit sketchy, I don't know. So the idea is the birth of dynamics out of statics. And I should say that both Santiago and myself were more or less orphans of catastrophe theory, because we were both in love with Tom and his ideas. And then, at some point, the fact that many people had, frankly, exaggerated in applying these ideas, put a discredit over them. And I think it was real bad, because the idea, this way of thinking, which was the idea that, in fact, pure thought could lead to really applied results, was nice, and there were profound things which had been done, of course, which were the singularity theory for maps, and which should have been done. And in fact, the way the mathematical community reacted to the fashion of catastrophes probably prevented some quite good mathematics to be done. So, in fact, some people were strong enough to go on, people like Vladimir Arnold in Moscow and his school, but for others it was harder, and so there was a splitting between so-called pure mathematicians who were doing differential topology or singularity theory, but nothing applied, and people who were doing very applied mathematics and maybe a little boring mathematics using the... So it was a pity, because I think the right place where one should work is in between. I mean, for a mathematician. That's where Arnold at his school were. Okay, so I will try to express this in a way which is more or less Tom's vision of things in some sense. So the idea is that you have, so it has to do with the, Tom was very, was really in favor of stratifying function spaces. That was one of his big ideas. And there is a paper of his in the lecture notes, which is the proceedings of a meeting in Amsterdam in 1970, which is about that. And he was rather violent, as far as I understand, when he gave his talk, but the written account is a bit more politically correct, but still what he says is that if you take, for example, the space of root of some Sobolev class, say, in R2, R3, R4, R6, and so on, it is the same Hilbert space. Okay? So from the viewpoint of functional analysis, there is absolutely no difference between the dimensions. So whether things are knotted or not, for example, you cannot see. But if you stratify your space, then you will see such things. Okay? And this has been very, this of course has been, this viewpoint has been really useful when Cerf gave his proof of the H-cobordism theorem, which was a functional proof. And later on, Cerf did his pseudo-isotopy theorem using the same idea, which was in publication de l'IHES, publications of the IHES. And much later, a student of Arnold who is called Vassiliev used the same idea to provide invariance for knots. So the Cerf thing was about functions, real functions on a manifold, and on the contrary, Vassiliev was about mappers from the circle into the manifold. Okay? But he was stratifying the space, and by looking at what happens between a given family of knots and the strata of this stratification, he could get these invariants, which is quite a nice job in topology. Okay, so here I will not go quite as far as that, but I will explain how first how the transversality lemma of Tom in jet spaces is proved. So the idea, so I take several cases. So my idea is more or less to give some taste of what happens for potentials. So potentials is the case of real function on the manifold. So if you're afraid of such spaces in the case of non-compact manifolds, then you can assume them compact, and then it's a quite reasonable Fréchet manifold, which is just the limit of the CK of MR, which are Banach manifolds. Okay, but anyway, it works also for this terrible topology which is called the Whitney topology, or for the compactor open topology in the non-compact case. Okay? So in fact, what happens is that this topology is terrible from the viewpoint of topology, because, for example, you don't get a topological vector space for the first. The infinity of MR is not a topological vector space for the Whitney fine topology when M is non-compact, because multiplication by a scalar is not continuous. Okay? But nevertheless, it is a bare topology, and this enables one to do transversality theory. Okay. So I take F to be either the space of potentials, so that is statics, you are considering potentials, and the other two cases are dynamics. So you consider the space of vector fields on M, or the space of maps of M into itself. Okay? And so here comes the notion of a jet. So you say that two maps have the same kth order jet at a point, so that if they have kth order contact at that point. So in fact, it's a notion which involves mapped germs and not maps. Okay, so what do? You are taking charts, and you see that the fact that they have the same kth order Taylor polynomial at the point you consider is invariant by chart changes. So that's the idea is due to Ehresmann, and you see that this space of kth order jet, so k is an integer, of course, it is a finite dimensional manifold. For example, if k equals 0, then gk of mr is m times r. Okay, just take a point and the value of the function at that point. Same for gk of m is m times n, and the second one is just tm. Okay, because when you have the value of a vector field, it projects onto the point at which you take the value, so to speak. Okay. And there is so you can think of M as a torus, in which case the kth order jet is just the kth order Taylor expansion. Okay? Okay? So the space in that case consists of one point of M and the Taylor expansion of the map you are considering. Okay, so the fundamental fact is that this map which to f and x, f is in the function space and m is in the manifold, associates the kth order jet of f at x, is a smooth submersion. Okay, so now we go into the, I will not, so it's perfectly correct if you are taking for f CR of MR with R a large enough integer, then it's true. In the usual sense on Banach manifolds, if M is compact, okay? But in fact, it's true in every reasonable sense, and you see that this map, in fact, it's local. So it means that it does depend on F only near X. And this is what is lost when you take functional viewpoints on the transversality lemma, because then you do not, you lose that. That's okay. Anyway, so what happens is that since that map is a submersion, it implies that for every submanifold of the jet space, its inverse image, which I note with I denote by tilde W, so W is the submanifold. It is a submanifold of the function space times the manifold with the same codimension as W. Okay? And now, if you so maybe what I am saying needs finite dimensional approximation. So you use the idea that a function space is a place where you can walk. Okay, so you take, instead of considering the whole of the space, you consider parametrized families of functions, and what you get is you can get quite correct statements in that case. But the general idea is really that. And so what happens is that the critical set of the restricted projection of this W tilde onto the function space is the set of those points Fa such that the case jet of F is not transversal to W at A, which means two things. The first is that the image of A by JKF is in W, and that the sum of the image of the differential of JKF and of the tangent space of the manifold is not the whole tangent space of JK. So maybe I should explain what this is about. Okay. Can you will tell me if you cannot read. So it's really simple. So you have let's say I have a function, let's call it pi, of two variables, x and y. And you assume that 0 is a regular value of pi. So what happens is that the inverse image of 0 by pi is a smooth curve. Okay? And now if you project, you are looking at the set of points at which this curve is badly projected onto the first factor. And clearly, it means that you cannot apply the implicit function theorem, meaning that the partial of pi with respect to y is 0. Okay? And what I have written upstairs is just an elaboration of this. It's not much more. Okay? Because you can locally represent W by yes. You can locally represent any manifold by an equation, and then you are more or less in this situation, except that you have more variables, maybe infinitely many. And now you have a theorem, which is due to Sard, which says that if you consider the critical values of pi, the set of critical values of pi is neglectable. It means that it is very small. So now, of course, here we are not in finite dimensions, but it's almost as if we were. Okay? Because first, in the Banach setting, Smale wrote an infinite dimensional version of Sard's theorem, which applies to that case for finitely differentiable maps. And moreover, it has been proved recently that, in fact, this set of functions is really neglectable in a more measure theoretic sense, because, in fact, you know that it's a problem to get a measure on a function space, a natural measure, but what is rather easy is to define what is a neglectable set. And this has been done by I don't know their name. There is York. Alexander and York? No. I should know. But it's in the bulletin of the American Mathematical Society, I don't know, some 10 years ago. Okay? So what I am saying is not pure poetry, it's true. Okay? And now if you think of it, the critical set of pi is the set of those points Fa such that the kth order jet of F is not transversal to W. And okay, so it means, thinking a little, that those points which are not in the image of this critical set, that is, which are not critical values, are precisely the functions F, so that the jet is transversal to W at every point. Okay? And moreover, if W is closed, then this set is open. Okay? So it's clear for compact manifolds, and it's true for the Whitney topology in the non-compact case. Okay, so now I am coming to the point of my lectures. So, you know, so imagine you are thinking that what is good in dynamics is statics. So you wish to be, when you are at an equilibrium point, then you wish to stay there, you are happy like that. Okay? Either you are lazy or it's some place, in some sense. Okay? Imagine you're in the case of a potential, you have a maximum of the potential. The potential is what you gain in a situation. You are happy with a local gain. You are not like modern specialists of finance who wish to have an absolute maximum. You're there, and then what I am going to explain is that you cannot live like that, unfortunately. Okay, so you can apply Thom's transversality lemma to the situation where the manifold sigma is the set of rest points of kth order jets of elements F of our function space, which have a red at A being a rest point of F. So I take the three cases. You have the case of potentials where you take k equals 1, because that's enough, and it's the places where the differential of which are critical points of the potential. Okay? And in the dynamical case, it's either a 0 of the vector field or a fixed point of the map. Okay, that's a rest point. Okay, and what Thom's transversality lemma tells you is that for almost every f in your function space, every rest point of f is non-degenerate. So that's the way transversality is expressed. So in the case of potentials, it means that the critical point of f you are considering is non-degenerate, which means that the Hessian of f is a non-degenerate bilinear form. Okay, and in the dynamical cases, it means for vector fields it means that the differential is invertible, and for maps it means that the differential of the map at the point minus the identity is invertible. Okay, and so what happens? If you think of of that proof of the transversality lemma, okay, what I'm telling is that what is interesting is what happens when you take the inverse image of manifolds by that map JK, which to a pair consisting of a function and a point associate the kth order jet of the map at the point. Okay, and so if you do that, it means that these rest points are non-degenerate, it means that Fa is in the open subset of sigma, of the set of the rest set, so to speak. It's consisting of those points at which the projection of sigma into F is a local diffeomorphism. So in other words, you can express okay, so you have that X is a rest point of a map phi for X close to A and I don't know if you say phi or phi close to F. You have that X is a rest point of phi if and only if X is equal to capital phi of phi, where capital phi is a smooth implicit function, so that's equivalent. So it means that non-degenerate rest points are robust. Okay, but now if you consider this functional viewpoint, you can do much more than just say almost every point is non-degenerate, because you can consider the complement of the non-degenerate rest points, so to speak. That's the couples Fa in your set or in your rest set, and you can, as Whitney and Tom put it, you can stratify it. So there is an easy stratification. That is, you can express it as the disjoint union of manifolds. Okay, and what are these manifolds? These manifolds, well, sigma. So I put tildes here because they are obtained by lifting manifolds in jet space. Okay, and sigma tilde C is the smooth submanifold, which consists of those Fas such that in the case of potentials, the Hessian, in the case of vector field, the differential, and in the case of maps, the differential minus the identity has correct C. And this provides a nice stratification. And now, what one can do with that, you can again stratify each of these strata. And what you get, you can, so I take only the first stratum, that is the one which consists of points where you have codimension 1. Okay? So it means that the in that case, you can prove something. You can express your manifold sigma 1 tilde as the union of manifolds sigma 1 C tilde and some sigma tilde 1 infinity, which is just the remaining part. And each consists of points where you have a normal form for the set of rest points around. That is, you have a family of charts on M at A, depending on the function phi you are considering, phi being close to F, such that a point in the domain of the charts C phi is a rest point of phi, if and only if you write its image by C phi as a pair YZ with Y in R and Z in R n minus 1, then it's given by the equation Z equals 0 and YK plus 2 plus the sum of the lambda j's of phi Yj equals 0. So this gives you forms, and what happens is that this is of course for finite k. What what have I done? Yeah, K is C, I think. Yeah, here it's K. Yeah. Okay. So that's sigma 1 C tilde is sigma 1 K tilde. Okay. So what you see is that and these phi are smooth and their differentials at f are independent. So in the case of k equals 0, you get what is called the fold catastrophe. That is, here you have only one lambda 0 of phi, and so you see that when this lambda 0 of phi is positive, you have no rest point around A, and when it is negative, you have 2. So it's the fundamental thing. You have matter and antimatter and so on. It's really the way critical points are born. Okay, and so in some sense, it's not really dynamics which is born at that point, except that when you are on the part when there is no rest point, the hammock in which you had been resting, it disappears. So you have to go somewhere else, and if it's a dynamical system, then you will have to follow the orbits, and it can be complicated. Also, what is interesting is that the complement of these sigma tilde 1k's has infinite codimension, which means that if you take a generic k-parameter family of functions, it will almost always avoid this set. Okay? So it means that you can think of it really as neglectable in every reasonable sense. And the whole idea of singularity theory is that things that happen outside such infinite codimensional subsets do not count, are so to speak, algebraic. You have algebraic models. That's what I have done here. Okay, so just in the end, I will explain another way for dynamics to be born out of statics. Okay, so I must say that this viewpoint of catastrophes, which is that you're looking at something more global, was really a progress with respect to what people in bifurcations were doing. Because if you assume, what they were doing is that they were following a rest point. They had a one-parameter family of functions, and they were following a rest point. And in fact, they had their nose on the rest point. And here you see you have two rest points that collide and disappear. And you cannot see that if you postulate. So what they got in that case, they had pictures like that, which corresponded to. So you have your fold like that here, and it corresponded to paths in function space, which are rather rare because they are tangent to the fold line. Okay, and then you take what's above it. So that's not very rare, but you need two parameters to have this generically. Okay, and if you view things like that, they become simpler, and you do not say that this will happen very often, because what will happen very often is either this or that. Okay, so I will stop just after I have explained. So now in the case of dynamical, in the case of potential, there is some kind of a miracle. It's that you have the Morse lemma with parameters, which tells you that if FA is in the rest set, then you have charts which transform every phi close to F near A into the same quadratic form plus a function of phi, a smooth function of phi. And this can be made into a global result which tells you that if M is compact, excellent Morse functions, that is Morse functions, all of whose critical levels are different, are structurally stable, meaning that if you have the group of diffeomorphisms of M and R act on both sides, every function near each one of them will be conjugate to the given function. So it's a miracle, and this in dynamics is not the case. In dynamics, you have points which are non-degenerate, that is, you have an equilibrium which persists when you perturb your function, and nevertheless, first you have no such model, and moreover, something else happens which is dynamics. So I will just give an example and stop. You consider I take the case of maps, so that's the simplest case, and you consider the manifold consisting of, so I called it sigma minus 1 tilde, which consists of points Fa when minus 1 is an eigenvalue of the differential of the of your function. Okay. So I am I also assume that the point is non-degenerate, that is, 1 is not an eigenvalue. And then I have a result which is absolutely parallel to the previous one, which says something new. It's that you can stratify up to some infinite codimensional subset. You can stratify this manifold in such a way that you have models for, in each stratum, so again C is K, you have in local charts, you will have that the periodic points of period 2 of your maps, that's the solution of phi 2 of x equal x, correspond in those charts to their set corresponds to the equation z equals 0 and y times a polynomial in y which has even degree and coefficients which are smooth independent functions of phi equals 0. Okay? So, in fact, you see that there is this, you get an even function for the set of real two periodic orbits, which is, and the action of phi on this is just take y to minus y. Okay? And this is the period doubling bifurcation. Okay? And so you see that what happens here is that out of a rest point which is non-degenerate, that is, which persists, an orbit of period 2 of the dynamics is born. So it's not much of a dynamics, it's just a Z2 action, but what happens is that you can prove that there are lots of points in that set of non-degenerate rest points of the dynamics at which you will have the birth of many kinds of invariant compact manifolds. And that was the title of my talk. And what you can get is circles, that's the Hopf bifurcation for maps, which actually is due to Sacker and Neimart. But you can also get all kinds of compact manifolds, including spheres of codimension 1. So for that you need at least 2 parameters. That's a dimension 2 situation. But you can also get the Santiago's manifolds. So we come back to these manifolds, which are not projects of spheres, and you can get probably all these manifolds which have been studied by Laurent Mersman, and so you see that they are born and they can be attracting, and they bear the dynamics near the point you are considering. So it's so far the dynamics has been essentially about invariant tori, and what this shows is that there is absolutely no reason to consider only tori as invariant manifolds, except that one can do it, and it's really difficult to go over the normally hyperbolic cases in general, but nevertheless, this is what we have been doing in recent times. Okay, so I think but that's what I was saying, that there is a lot of work to do before because every time you discover a new phenomenon from an abstract viewpoint, and it's generic in some sense, then it has to happen in nature. So now after that you have to go to natural systems and find what has happened, that it does happen, and it's not so easy to do that, because if you have very complex systems, you never find anything that you are not looking for, and so if you do not first try to do a mathematical theory to have some morphologies you can identify, then it's hopeless. You will not be. People find what they know they can find in general.
Any other questions?